Good morning, good afternoon, good evening, good wherever you are, and welcome to another SNIA presentation. This one is from the SNIA Compute, Memory and Storage Initiative, and we're going to be talking today about some of the work that the initiative is doing, and also some of the technology and interesting things that we're going to be doing over the next 12 months with this collection of technologies that have a great deal related to each other. We're going to be talking about uniting that compute, memory, and storage set of technologies, obviously all with a storage bias. So today I'm joined by, I'm Alex McDonald, by the way, from NetApp, but I'm the co-chair of the SNIA CMSI. But today I'm joined by Ellie Tiomkin. Ellie, say hi.
Hi.
That's very brief. Thank you very much, Ellie. I'm sure he's got more to say for himself once we're into the presentation. We're also joined by Jonmichael. Hi, Jonmichael.
Good morning, guys.
And last but never least, Jim Pfister. Hi, Jim.
Yeah, good day to everybody. Thanks for having me today.
That's really good. So, before we get into the body of the presentation, just a few administrative items. What you have in front of you is a screen with currently the legal mumbo jumbo that we put at the front of every these presentations, and that mumbo jumbo basically says that this presentation is copyrighted SNIA. We'd like you to be able to use parts of this, but do so in terms of the copyright we give you, and that there are no warranties for this. If whatever you touch it with breaks into two parts, both of those parts are going to be yours. In terms of the interface, there's a couple of things that you may not be aware of if this is one of your first times at a Bright Talk. First of all, you can expand the screen to full size, so you can actually see more of the screen. And on some of the presentations that we do, and perhaps this one as well, you'll find that some of the text is quite small in a standard size window. So making it full screen enables you to see more of that detail. The second thing is that you can actually ask us questions during the proceedings. There's a button there that you can press, you can ask us a question, and if we've got the time, and if it's appropriate, we'll answer the question during the presentation. Failing that, I'll point you to our website at the end where we'll take all the questions and write up a quick blog entry so that you've got some reference to the question that you asked and some answers from us. And we also have a feedback button. We're always desperately interested in feedback. We really want to know what you think of what we're doing here, and comments in particular are always welcome. The feedback goes from 1 to 5. 1 is, gosh, I wish we were doing something else. And 5 is, I really like this lockdown stuff. More, please. So rate us as you leave the presentation today on that 1 to 5. And lastly, we will be providing a copy of the slides. So if you're wanting a copy of the slides in PDF form, you will get a link at the end that allows you to go and retrieve them. SNIA is an organization that perhaps, as you know, is 185 industry-leading organizations. We've got over 2,000 active contributing members, of which we, Band of 4, are part. And we've got also 50,000 IT users in storage and other environments who follow us on Twitter, follow us on the web, and also use materials like this for their education. So welcome to you today to this presentation. SNIA's areas of focus include quite a lot of different technologies, and we try and organize them in related groups. So we have things like storage management, for instance. We've got a group that's involved in cloud storage technologies. And we have this group. This group is to do with the compute, the memory, and the storage interface of CMSI. And we'll talk about a little what we do and how we're shaped as we go through this presentation. But each of those groups is providing its own educational materials under the framework of SNIA and making sure that we take out a common set of messages about what the industry is doing. So our topics today, and the CMSI is proud to present, for the first time, we're going to be talking about computational storage, one of the parts of the group that this initiative covers. And secondly, we're going to talk about solid-state storage and where that's headed. And last but not least, we're going to be talking about persistent memory, a new technology that allows us to have memory that looks like storage. In other words, it's persistent. And finally, We're going to talk a little about why SNIA brought these activities together and what it means to play nice, how we actually make sure that we can represent these, what appear to be disparate technologies, but really aren't, in a single group and provide you with the kind of information and educational material that you're looking for. So without further ado, I'm going to pass over to Ellie Tiomkin, who's going to take us through computational storage. Ellie, take it away.
Thank you, Alex. So welcome everybody, and I'm going to be covering computational storage. So when you look at computational storage, definition by SNIA, computational storage defined as architectures that provide computational storage services coupled to storage, offloading the host processing and reducing data movement. And the first question that comes to mind is why? Why do we need computational storage? Why do we need compute capabilities inside the storage? CPUs and GPUs are doing a wonderful job as the host. And there are a few reasons for that. One of the main reasons is data growth. We're all aware of all the ever-growing data that is coming our way from IoT, 5G, and many other sources. And with the vast amount of data, the ability to compute the data becomes a challenge, mainly because the data needs to move between the storage and the host memory for the CPU, GPU calculation. On top of that, a few other reasons why the computational storage is needed. The concept of bringing compute to data is not new, but mature technologies such as PCIe, NVMe protocol, and FPGA CPU technologies came to a crossroad where we can use them inside the storage and enable computational storage. So the basic compute storage architecture has been the same for many decades, going all the way back to tape and floppy and hard disk drives, and even solid state drives. And we're looking for ways to innovate and make compute easier within storage capabilities. And what the technical working group at SNIA came up with are 4 different use cases of computational storage, and I'm going to walk you through each one of them. So on the left, we have an FPGA connected to a bridge that connected to a standard SSD, all within one package. The second example is we have an FPGA that is connected to a standard SSD, all within one package. The third example is an FPGA and RAM that sits on the fabric of the PCIe bus and processing the work. The actual unit has no storage, unlike the other first 2 examples. And last but not least, we have the SoC, the system on chip approach, which we have an SoC that is from one plane managing the flash into an SSD, just like any other SSDs in these examples or elsewhere. But there's a second plane inside that SSD with the compute core that is dedicated for computational storage. Now, each one of these 4 examples has behind it vendors out there in the market that deliver products today that is readily available. And the common thing between all these examples is that each one is bringing the compute to the storage, and the side effect is massive data movement reduction between the storage and the host. And that's one of the main benefits of computational storage. So in SNIA, there's a technical work group, the TWIG, that has 45 participating companies, over 200 members. And the TWIG initiative is to develop computational storage architecture and programming model, defining recommended behaviors for hardware and software, and support computational storage. That TWIG is in existence for about a year and a half and gaining a lot of traction out there. If you take a look at the 45 participating companies, you'll be able to find, first of all, the companies that actually do computational storage products or services today and sell them in the market. But on top of that, you'll find the CPU manufacturers, the 6 NAND companies out there, and a big participation from the ecosystem around storage systems and networking. And with the TWIG under SNIA, we have now the SIG, the Special Interest Group, where the SIG is working very closely with the Technical Working Group, where the main initiative is education. So educating the market, presenting, doing webinars like this, and spreading the word of computational storage to make sure that companies are aware of this solution and can take advantage of that. And I believe that was my last slide, so I'm going to turn it over to Jonmichael, who's going to talk about the solid-state storage. Yep.
Elliot, before you do that, just a quick question. In terms of computational storage, one of the things that was quite popular about talking about a few years back was composable storage, where you could actually go out there and you're basically requesting the system, you know, I want a bit of storage and I want something that's going to do compression and I want something that's going to do RAID and I want to be able to plug this together in some software-defined way. Is that one of the parts of what the group is going to be looking at as well?
Yeah, so part of this, the computational storage services that the TWIG had defined, you can have a built-in storage service that is doing one purpose, for example, compression or encryption, that you get that built into the storage that you're buying, and that computational storage is constantly doing that function. Another service is an easier programming model where you can take a service for compression, but then use that computational storage device to do other things such as processing images or videos. So you can have two different types of services that can be run on computational storage. One is set ahead of time, and the other one is programmable.
Okay, good. Thank you. Thank you very much. Sorry, Jonmichael, over to you.
All right. Hey, good morning, guys. So this is Jonmichael Hands. Many of you guys may know me because I also co-chair the NVM Express Marketing Work Group. I'm a product manager and strategic planner at Intel, and I recently got nominated last year to co-chair the new SSD Special Interest Group, and if I can ever get the acronym right, for the CMSI. But so we kicked off the SNIA SSD Special Interest Group last year. Cameron Brett of Kioxia is the co-chair with myself, and we have been tackling lots of SSD topics. So there's lots of interest, especially we got a lot of interest in the NVMe marketing work group from topics like form factors or topics like SSD segmentation and topics like SSD performance. But NVM Express doesn't cover those items because we're really focused on the NVMe technologies and the specification and the features. I don't really care about form factors or physical interfaces per se. So one of the things we've been trying to do with this new SSD special interest group is kind of combine all the stuff that's going on in all the various technology work groups, for SSD technology. So one of the big things is form factors. So we just rewrote the form factors page up on SNIA, as many of you guys have noticed. I've included the link here, but you can just Google SNIA SSD form factors and it will show up. We have added some graphics for EDSFF. I've written an entire EDSFF section. We've updated the add-in card and M.2 and U.2 sections with all the different specifications and standards. So take a look at that. And we want that to be a good reference and living document for all the form factors that are being actively used for SSDs. And then some of the other things that we're going to tackle in the future of this work group is trying to do more segmentation around SSDs to help people understand different classes of SSDs. So I think we do see some difference in features and power and performance and quality of service between, for instance, data center drives that are used in hyperscale cloud, between enterprise server OEMs and mainstream server use cases, and then between storage and high availability dual port use cases. We are seeing different divergence of feature requests and form factors and capacities and media technologies. So we are going to try to help tackle some of that in the work group to go be able to actually use real performance data and real drives to kind of show the differences between different drive classes. So today I'm going to give you guys, because SNIA is owning the EDSFF specifications now, I'm going to give you guys a quick update on kind of what's happened. This is the same slide I presented. I actually kicked off the EDSFF overview track as part of the OCP storage workgroup in the OCP Virtual Summit. So I got the pleasure of representing SNIA and OCP storage workgroup of giving the EDSFF overview. So there's been a ton of work in OCP on EDSFF, but here's kind of the generic timeline. So there was at one point an EDSFF working group in 2017, and I was the product manager for the Intel ruler at that time. And then we were launching that at the end of 2017 at the Flash Memory Summit, and then we actually kind of contributed all that to an open standard because we saw customers really were super interested in the form factor, but needed it to be an industry standard. And then the EDSFF work group that was kicked off to kind of go redefine what data center SSD form factors look like, well, that didn't really make sense to keep that going. It was not meant to be a sustainable new work group. We already have way too many technology work groups. So all that work was donated into SNIA SFF. And since then, you've seen the SNIA SFF has actually published 3 actual specifications for the EDSFF form factor drives, so the E1.S, E1.L, and E3. And we have the TA1009, which is actually the pin and signal specification that kind of combines all the EDSFF family, so they have one common pin and signal definition, and then they all use the same common connector, the SFF TA1002. So all these are part of SNIA, and I'm going to talk a little bit about what kind of some of the new stuff that's going on in EDSFF is. So the good folks at Dell, Bill Lin, had sent me this updated slide, so thank you, Bill. He is driving the new changes in the SFF TA1008 spec, which is the E3 family of specifications for a 2U optimized EDSFF devices. So as you can see, the E3 actually has 4 variants. Now in the old spec, it was called, there was a short, long, thin, thick. We're kind of moving to this new naming convention where there's a 1X and 2X device, for 1X being the thin and 2X being the thicker one. And the intention is that they're fully interoperable. So if somebody designs a backplane that supports the 1X, you can plug a 2X device in and it just kind of covers up the other slot, and vice versa, where if somebody has a slot that supports it thick, it has a common rail, and it's an asymmetric design, so you can plug a 1X device in there. And then the different variants, now for SSDs, we expect, kind of most of the SSDs to be on that 3/4 length one, which one you're kind of seeing closest to the picture. And then there's 2 different variants of that. There's that thin one, the 1X device, which is a 25-watt device, which kind of is similar power envelope to U.2, but will get us a little bit higher capacities and board real estate for some of the new PCIe Gen 5 devices, and as well as supporting, you can see it supports the EDSFF connector, the SFF TA1002 for by 4, by 8, or by 16. And then the thick device will get you to up to 40 watts is what the spec is currently specifying for this 2X device, which will allow for storage class memory, for persistent memory on the CXL interface. It'll allow for much higher power accelerators. We maybe want to scale the PCIe bandwidth to support higher. So really, this opens up the door, as many of you guys know, OCP NIC and other devices use the same connector. So this kind of opens up the SSD form factor to more other device types, and this is really exciting. Obviously, Dell and HPE gave a presentation about this at OCP, so I encourage you guys to go watch that in the virtual summit to learn more about what their thought process is. But they've spent a lot of time really trying to make this a form factor that will last, at least the next 10 years out through PCIe Gen 5 and Gen 6 and beyond, to be really the general purpose 2U form factor that replaces U.2. And so the spec has been updated in the draft. If you are a SNIA member, you can go into the SFF work group and look at the 1.01 version. It's really more like a 2.0 version, right? Because there was quite a few changes. You can see they changed the LEDs, they changed the naming, which they're still working on. We're still trying to figure out what the naming convention ends up looking like, and as part of our SSD work group. And then they've changed the connector registration point to support the use of an E1.S PCB in an E3 enclosure, and all kind of go more about that here in a few slides. But yeah, a lot of awesome stuff going on in the E3 spec in the last couple weeks.
Jonmichael, can we stick with thin, thick, little, and large? I can't remember what you called them. I know they were much more descriptive.
Yeah, that's you know, this is what happens sometimes when technical work groups try to do the naming. You know, we would love to talk about this in our in the SSD SIG, because that's part of you know, the original EDSFF naming came. Boy, I was involved in the U.2 naming, and I was involved in this EDSFF naming. It was not easy to come up with a name. It sounds easy now. E1, you know, was optimized for 1U form factors, and we wanted to do an E2 for 2U optimized form factors. But I digress. We have, yeah, boy, yeah, I don't even want to tell you how much time I think about this, unfortunately.
I beg your pardon.
It would be sad. So the other thing that's new, as you guys have seen, the SFFTA 1006 1.4 version, it has been posted, and that includes this 15mm E1.S variant. And I talked a little bit about OCP, why Intel and Microsoft think this is a really cool thing. So one, you know, EDSFF is really your cloud-optimized form factor. The E1 class of form factors for EDSFF is really optimized around cloud first, because the cloud uses 1U form factors. They use 1U servers and 1U storage arrays. So having a 1U native form factor is really awesome. And you can imagine if you have a 9.5mm E1.S, you can fit 32 to 36 of those devices across the front of a 1U. So with 15mm, with a standard pitch, you can fit 24 devices across the front of a 1U, which is, you know, 2.4x the amount of I/O you can do with U.2 by using the drives horizontally in a 1U. So it's significantly higher performance as far as I/O performance in a 1U server. And then this new form factor, the 15mm heatsink, allows you for per drive power to go up to, you know, 35 watts. Now the spec says 20 watts at a certain airflow, but if you simulate, I'll get into some of the thermal stuff in a few slides, but there was a great presentation at OCP on this whole thermal methodology. But you know, we've simulated up to 35 watts at 35C, and seems like that might be acceptable for, you know, standard server configs with standard fan speeds, which is awesome, because this means you can do a higher performance, higher power than U.2 in a smaller form factor. And this will allow you for really scalable form factors for PCIe Gen 5, for storage class memory. Obviously, Intel loves this for our future Optane, because higher power and more performance is great, and supporting PCIe Gen 5 and beyond is really awesome. I mentioned that, you know, the CXL interface runs on PCIe Gen 5 electrical, so this would make a great candidate for, you know, persistent memory on the CXL form factor. And, you know, for even just mainstream TLC NVMe SSD capacities like 4, 8, and 16 terabytes will be kind of the next 2 to 5 years of mainstream capacities. This actually seems to be adequate as far as power and performance. So, boy, a lot of interesting stuff, and I'll talk a little bit more about why I'm so excited about this.
So just a quick question from the audience. Thanks for the questions. Keep them coming, by the way. Is E3 backward compatible with E1.L or E1.S?
It's the same connector, and now, so if you had, so say you had some testing infrastructure that supported an EDSFF connector, you could plug in any of the variants of EDSFF, so E3, by 4, by 8, or by 16 into a by 4 slot. You could plug in an E1.S or an E1.L. Now, on a mainstream actual deployment server, E3 is actually meant to be used as in a backplane, where E1.S and E1.L are meant to be used with either an orthogonal connector or a backplane. So, yeah, the answer is sometimes.
Sometimes, okay. And the secondary question, sorry, go ahead, Jonmichael.
Oh, yeah, no, go ahead. You can read the question, Alex.
Yeah, no, it's just, will E1.S be an alternative for larger capacity NVMe drives in workstation class laptops? I suppose replacing M.2. So the question, I think, is about where we're going with M.2 as well.
Yeah, my personal opinion, right? So, you know, M.2 is kind of taken over client space, right? There's like 100 million NVMe drives sold or something in 2020. It's the numbers, some absurdly high number, right? So M.2 is really the dominant form factor for laptops and desktops and workstations, which to me is ridiculous, right? So if you have a 300-watt GPU and, you know, a 200-watt CPU, are you really going to get the best performance by using an 8-watt M.2? No, absolutely not, right? We've proven in data center drives at a 4 terabyte and 8 terabyte drive, you know, going to 25 watts and higher will give you much better performance. You know, not trivial amount of performance. We're talking about 3 to 4 times as much performance as an M.2. So will this be used in main workstations and high-end desktop? I sure hope so. It's chicken and the egg, right? Spec. Now that the spec exists, and now that SSD vendors are going to be producing these drives for the cloud space, I really hope that there's people out there making workstations. Again, I work on a data center SSD roadmap, so I unfortunately don't get to be in all those conversations, but I've certainly been having conversations with many people at Intel about this topic, and we are, yeah, I will just say my personal opinion is that it makes sense to me.
Okay, thank you.
Okay, so the next couple slides are really just kind of a, sorry, I hope I didn't click the button too many times, are kind of a summary of what happened at the OCP Virtual Summit. So I made kind of, this is my one slide of just some of the new platforms that were shown off for EDSFF. So as many of you guys know, you know, Samsung showed off an E1.S of their new PM9A3 SSD and a Poseidon reference hardware for disaggregated storage, which really uses lots of cool stuff in NVMe and NVMe over Fabrics and EDSFF, of course, in the platform they partnered with Inspur. So just for anybody out there that is wondering, you know, the form factor wars are done. The industry has chosen EDSFF, and all the SSD vendors and all the mega cloud providers are on board. As you saw, Dell and HP are, you know, have provided contributions to the E3 spec, and so the next generation of form factors for SSDs is EDSFF. If there was any confusion from anybody, now that's alleviated. So now the new designs for EDSFF. So you can see Facebook they showed off two platforms. They showed one of their sleds that has this Yosemite V3. It's a compute nodes that has support for 4 E1.S, 25 millimeters, and then they have their mainstream 2-socket cloud using the Intel Cooper Lake CPU that they showed off using, and there's 4 slots for E1.S 25 millimeter that you can see with my little arrow, my fancy arrow technology. And then in the keynote, Microsoft didn't really talk about it specifically, but we did talk about in the Intel keynote support for the OCP Cloud NVMe SSD spec, which, you know, specifies EDSFF as the preferred form factor. And Microsoft did show off their new secure control module on their new next-gen server platform design. And you can see here, kind of snuck in there, with these 4 EDSFF slots. These are E1.S 15 millimeter on the next-gen Microsoft platform. So that's exciting. And if you watched Jason Adrian's presentation from the OCP Virtual Summit, then you'll know he highly endorses EDSFF as kind of the preferred form factor. And he does a good job of explaining kind of why they've chosen E1.L for, you know, QLC and large capacity drives, because it's a long form factor, it's big, and it has high capacity storage. And then that's why they've chosen kind of E1.S 15 millimeter as the preferred kind of scalable building block for next gen hyperscale design. And then this was a slide from my dear friend Ross at Facebook, and he was showing the E1.S SSD vendor ecosystem. And, you know, so these are some prototypes from some of the different SSD vendors. You can see you got the big ones, Samsung, Intel, Kioxia, WD, Micron, you know, make up, we'll say, I don't know, I think like 80 or 90% of SSD, you know, revenue and volume in the data center. So having everybody, these guys on board with EDSFF, it's really awesome. So it's good to see that Ross pulled this together. Now I think that there's still, as you guys see, there's different options for heat sinks in the EDSFF family, but you know, don't confuse them for different products. Really, you know, vendors can take the same product and put different heat sinks on them, and it's really all part of the same EDSFF family with just different options for different thermal boundary conditions, different airflow, which kind of brings me to, if you are interested in this, our Intel expert on the subject matter, Paul Gwynn, gave a great talk at the OCP about thermal methodology for EDSFF in actual servers. So looking at the 9.5, 15, and 25 millimeter symmetric and asymmetric enclosure options for EDSFF, and looking at the different power, different airflow, and different platform impedances, and looking at what the actual power and airflow requirements would be. So a lot of, if you guys are interested in thermal capability of EDSFF. There's I can point you guys to that presentation. Was very, very good information about, because we've been getting a ton of questions about this from customers about, what power level do these different drives support, and how much air fan speed do you need and whatnot. So this was a very good methodology of how they came up with different platform requirements. And again, different customers are going to have different platform requirements. For customers that want best performance, and most I/O, they might want to go to the 9.5 millimeter to fit the most drives in a 1U. If a customer has a design where they might just want the best TCO and lowest fan speed, they might go to a 25 millimeter. And then that kind of leaves 15 millimeters, that sweet spot between kind of a good compromise of both, where you have really great performance, power, and scalability, and pretty good airflow. So, all right, so that was what I was talking about for the SSD SIG. Again, I mentioned a lot of focus on EDSFF and form factors right now. That's because we own the marketing and stuff for EDSFF, and there's going to be a ton of more work. So if you guys are interested in the members of SNIA, please join our SSD SIG. We've had some great calls and talking a lot about all the new exciting stuff going on in SSDs. So.
All right, if you would like me to take it over and have a conversation about persistent memory. There we go. Ellie was talking about the computational storage pieces and how that is fitting together into a larger storage area, and then we moved down to the solid-state drives, really looking at the drive mechanisms itself. I'm going to go down and out in terms of where we're headed in CMSI with persistent memory. You think of persistent memory as basically a non-volatile, byte-addressable, low-latency memory, which essentially gives you the core technologies that are going to be used not only in SSDs but are also going to be used in the larger computational storage devices. But realistically, persistent memory can take on its own tier as well. And when SNIA first took up the persistent memory handle, the intent was to really expand from the SSD and move it up a tier and move it up parallel to the DRAM or just behind DRAM in order to be able to get you storage at a new tier with a different performance metric. Now, persistent memory can take a variety of different types. There are JEDEC standards such as NVDIMM-N, and that's effectively a DRAM DIMM backed by flash memory with a fairly complicated but elegant battery solution to be able to persist data during a power failure or some type of crash. There are other NVDIMM standards that are out there that that have been superseded by NVDIMM-N or that will supersede NVDIMM-N long term as the NVDIMM JEDEC standard moves along. And there's also a variety of other great technologies out there, the MRAM, FRAM, PCM. SNIA has a series of very excellent talks by people who are deep into memory technology. And you could look up our old Persistent Memory Summit and pull down some of the presentations from that area to get an in-depth on the bits and bytes and gates and such of the various technologies. But the key thing that SNIA wants to do is not only advance these technologies, but also advance the use of the technologies in a very common way. And that's really where a lot of the persistent memory support has been the focus from SNIA. So that would involve defining the hardware standards. So like I said, JEDEC standards such as NVDIMM, we want to be able to support that early development. We want to understand how we can deliver requirements to the ongoing conversation around that, and then help define form factors and the interfaces around it. Where SNIA really comes in, though, is focusing on the software support. When I was first working with SNIA, long before I joined the organization as a contractor, we came to SNIA from my company and from other companies saying we think an industry standards body is the place to really define the verbiage for how the operating system support would come in, how we would want to go structure that, and then what we would develop in order to be able to advance all of the technologies in a similar direction. So defining the verbiage for operating system support, both closed source and open source, was one of the first efforts. Actually looking at how to standardize the verbiage into an open source library was the next. And then where we're focusing now, and we'll get into this as I present, is how we actually get more application support for the libraries and for the programs that we're moving on. So to that, I'm going to talk about a couple of technical work groups as well as a special interest group. So the first group to talk about is the SNIA Persistent Memory Programming Technical Work Group, or TWIG. And this is where the industry first came together to develop the persistent memory programming model. We wanted to talk about a set of behaviors, or as we would call it, verbiage, for how the software interfaces will provide access to non-volatile memory. And you can see the summary of that contained here in the slide. Effectively, the application can call a common library, and there are different paths that you can take through the library to address the persistent memory device. Again, there's some in-depth presentations that you can look at both on Bright Talk as well as from the SNIA Persistent Memory Summits that will go into this a lot more. But realistically, we wanted to provide a variety of paths. We wanted to be able to access the memory in a similar way that SSDs do today, and that's a driver level interface. We also wanted to be able to create a persistent file system that sat in memory itself that could be accessible. And so this would allow basically cache line addressability to a extent file system in the operating environment that would allow you to directly access the memory from cache, or there's direct memory accesses as well going directly to the PM devices. So the technical work group has been in existence for several years now. It continues to tweak a lot of the specifications, but realistically, a lot of that work is being done as new physical technologies are available. We make sure that the TWIG responds and makes sure that any adoption or any modifications to the spec can be done in order to be able to support those technologies, as well as then expanding some of the various interfaces up at the application level. There's another technical work group, and this actually spans not only persistent memory, but to what Jonmichael was talking about around SSDs, and eventually we believe that this will support some computational storage efforts. So this is the SNIA Solid State Storage Technical Work Group. We call it S3, so the S3 work group, not to be confused with the former video company. So what this TWIG focuses on is SSD drives, persistent memory, and SSD system work groups. This is mostly focused on performance and behavior. So there are some member companies that will provide real-world workload analysis, and that will allow you to be able to not just create a synthetic workload and be able to test your driver, your memory subsystem, but it will actually monitor the actual performance of an application as it's running. And some of these real-world workloads will actually span days worth of work, looking not at the specific I/O accesses, but at the behavior of the I/O subsystem itself, so that you can determine where your performance really is focused. Just on this, a synthetic database workload is typically, an 80% read, 20% write type of workload that is designed and run, and it can give you some basic database performance. But how about if your database has a backup in the middle of the night? Or how about if your database is actually being accessed by a variety of sources that are doing a different read-write characteristic, or more importantly, a different block characteristic access? This is where the S3 work group can really come with performance test specifications. And the focus of the group these days is really, like I said, expanding those performance test specifications, not only to the SSDs, but also into the persistent memory subsystem, and eventually into the computational storage subsystem as the technical work goes farther on that. So this is a way to be able to take a single reliable set of tests and be able to expand it across your entire memory and storage subsystems. And it's a very interesting place for SNIA to be able to focus and deliver value. And then from a special interest group perspective, we have the SNIA Persistent Memory and NVDIMM special interest group. So NVDIMM is obviously the JEDEC standard, and we want to make sure that we continue to support all the industry standards. But there are a variety of persistent memory technologies that are not memory standard technologies, but that still have adopted and perform to the open source libraries that the TWIG has defined. So, for instance, something like an Intel Optane data center memory will use the persistent memory development kit just like the NVDIMMs do as well. And so any of those technologies can actually use and will perform adequately using the same application. So the application can call the open source libraries. The open source library will differentiate what memory you're actually using and will allow the application to perform. What's interesting from the SIG perspective, as well as from some of the technical work group perspectives, is that you will see different performance characteristics as a result, and I'll get to that in a slide or two. But obviously the SIG, we formed it to accelerate the awareness and adoption of the programming model as well as persistent memories overall. And so we educate on the various types and benefits. We communicate the usage of the programming model. We can influence and collaborate with the different middleware and application vendors, many of whom are SIG members themselves. We can develop case studies, best practices, help set industry requirements. And we can coordinate with the industry standards groups on how to take those industry standards and actually get them to market, again, supporting the application base that's already out there. And by communicating that taxonomy, SNIA is really adding value into how we would want to move the industry forward. Now, but I'm glad we said exciting rather than interesting. 2020 has been a very interesting year for everybody, but for persistent memory, it's a very exciting year. We have been expanding the persistent memory programming model, and you can look at the different forums that we've been doing in the CMSI around non-volatile memory programming. We developed and added a library for the hardware threat model. We've provided some white papers for remote access for high availability. So this would now actually be able to use persistent memory in a network and do remote access to persistent memory if your system doesn't have it. And then also an atomics and transactions white paper digging further into the programming model itself. We have been running a persistent memory summit at SNIA, and we had our most recent one in January of 2020. It was one of the last live events that I know I went to before I was confined to the four walls of my house. We do have the slides available at the PM Summit. Again, if you want to see the programming model, the latest in the PMDK library, the latest with memory technologies, or what we've been doing with some of the different programming challenges, the PM Summit is a great place to be able to go, and would certainly encourage you to look at some of the videos and presentations there. And near and dear to my own heart, we've been focused for about the last 18 months on actually developing and leading a training program for software developers. We've been calling it the Persistent Memory Hackathon. We'll probably be changing the name a little bit over time. People love to hack, but they also love to learn. So we'll be offering not only hackathons where you can get availability to a system, but we'll actually be using those systems also to do training boot camps, as well as workshops and some additional programming challenges. So what we really want to focus on is ensuring that we've got the consistent Windows and Linux programming model that is available through the PMDK is something that you can use. There are other open source tools and libraries that you can also utilize, different file systems as well. But we are going to continue that hackathon and boot camp program. And so far, in the first year, we trained over 300 software developers on different programming, on the different programming models for persistent memory. Most of those were done at live events. We have been working on cloud-based models. We actually did an NVDIM challenge that I'll talk about in a bit. That was available from systems that sponsors provided, and we provided those through the SNIA Tech Center. Within the next month or two, I actually expect a common cloud provider to be able to have systems available for us, and SNIA will actually be providing through a cloud provider that many of you will be familiar with, systems available so that we can actually take these boot camps and workshops online. We don't want to wait for another live conference. We had a couple of good ones this year already at the Persistent Memory Summit as well as the SDC EMEA, but we also want to take this program online. If you enjoy looking at what we're doing in CMSI, I imagine you'd also love to play with what we're doing around persistent memory. So stay tuned and watch the SNIA blog for some announcements, like I said, for some online boot camps and some programming challenges. We did have one NVDIM programming challenge already, and we announced a winner, and there's a Bright Talk available for that to see the 3 misses hash table that Alex, myself, participated in. And I just wanted to say, long-term, where do we want to go with TM? Well, we'll be continuing to take it into new application spaces. And, you know, I just picked one out so that we could talk a little bit about where we want to go. But one of the first questions that I asked when I came on about a year and a half ago was, well, what new application spaces do we really want to address with persistent memory? And last fall, Arthur Sinio and I participated at the In-Memory Compute Summit. Arthur actually presented why you would use persistent memory for something like AI and machine learning. Typically, when you think of AI or ML, you're thinking of a live environment, mostly DRAM-based, and occasionally saving your data off to disk. But what we really want to do is take advantage of what AI is really good at, which is reducing your overall time to discovery and insight, and find a way to be able to use persistent memory to make that better. So looking at some of the I/O and computational performance needs of an AI workload, we think that persistent memory is a great opportunity there. And when you start to see, you know, we identified here as a storage class memory in between DRAM and the SSD, we think that there's some really good opportunity. And we've started to see a lot of the AI and machine learning companies pick up PMDK and begin to experiment with it. So I think you'll see a lot of effort end of this year and beginning of next year on driving persistence into artificial intelligence and really gaining some value out of it. So why don't I hand it back over to Alex, and let's actually tie all three of these things together and show you why we're so excited about CMSI.
Thanks, Jim.
And I can, okay.
And thanks, Jonmichael, and to Ellie too. There's one thing I want to do, though, before we do that, and that's to deviate slightly sideways, because Jonmichael got me all excited to think that we were about to start naming things in a way that made sense to me. I mean, I've been very impressed by the SpaceX program, and I'm particularly impressed by the fact that the recovery barges are called things like, Of Course I Still Love You. What's the other one called? It's got a really weird name as well. Just read the instructions. I mean, that's what we should be calling stuff. I mean, CMSI, yeah, okay, there's 4 letters. But it really doesn't summarize up what we're doing, which is what I'm going to try and do now, badly. But here we go. So what a combination.
Well, you know, Alex, I just wanted to comment, we could do like thin and thick and other things like that, but then you're going to make me think of milkshakes, and I haven't had lunch yet.
Oh, dear. We can't be having that. So what I'm going to do is just try and tie together these, what appear to be 3 disparate pieces, but really aren't. I mean, obviously there's a fundamental connection here, and that's storage. But there's a reason more than just the storage elements for bringing them together. And if you look over the last few years, and discounting 2020 as a complete disaster it's been, over the last few years, what we've seen are enormous developments in solid-state memory, including NAND. It's not just persistent memories based on other fancy physics, but also the NAND technologies that we all know and love. And these emerging memories have made us look at storage in a slightly different way, in that we're now thinking about things like, for instance, memory-based systems that are actually storage. In fact, for me, it's a return to boyhood, because my first job was on an IBM mainframe where we had real core memory, and when you paired the machine off, the core did not go back to all zeros or all ones. It actually remembered where you were. So at the same time, we've got this semiconductor scaling has slowed down. We're at the point now where getting much more horsepower out of a single core CPU, for instance, is actually fairly problematic. And we've been kind of stuck. Moore's law has kind of caught up with us. And I know we've got fabrication coming down to the 7 nanometer level, but we're still we're not pushing the way that we did. We're not seeing a doubling every 18 months, that's for sure, in terms of power from things like single core. So we're seeing a lot more parallelism. And that forces us to think about where we put the compute. Should the compute be, as it has perhaps traditionally been, in the center, and the data all goes to the center to get crunched and variously transmogrified, and then pushed back out from the center to the edges again? The answer, I think, is no. I think we're going to see an awful lot more compute at the edge. And that makes completely different demands on the way our storage systems look, are configured, how they smell, feel, touch, operate, all those kind of things. So this mixing, this combination of processing and memory and storage has created a whole menagerie of compute architectures, and that's what the CMSI is trying to make sense of. We're trying to pull these things together, make sense of them, and to actually make sure that we can explain these new technologies and how they apply to the real world in terms of the problems we're trying to solve. On that note, I'd move to the next slide, which simply says we need to play together, and that's really what we're trying to do here. We've been talking about twigs and SIGs, and I think the important thing for us is that a SIG, which is the tech marketing, if you like, of the work that a twig does, or the technical side, allows us to educate people on where we're going as an industry with these things. And if you look at the right-hand side, and if you remember the pyramid that Jim showed of the various latencies, this is just the same diagram laid out a slightly different way. And we can lay computational storage over the side, but we're providing that with solid-state devices, and we're providing that with non-volatile memory, persistent memory, and we're providing that with compute as well. So it's a new and novel thing for us. So the solid-state storage initiative, which is what we're originally called, or the SSSI, there are so many S's in this business, it's actually quite tempting to say that we should just call, Jim talked about the SSS, which is the 3 S's. We've also got the anyway, too many S's. But the CMSI has come about from the ashes, if you like, of the SSSI, and we've formed together to provide you with this bigger and better way of actually partitioning up what is fundamentally stuff that works together. So this gives us a real opportunity to talk about the way that we're organizing these fundamental technologies. So the CMSI is organized in much the same way. And I think we're going to do a pretty good job over the coming year in terms of talking to solid state, in terms of talking to computational storage, and in terms of talking of persistent memory. There's a huge amount to tell. These are really dynamic and fast-growing areas. And I think that we are really well placed to write this new chapter in terms of storage and memory. I think, and compute, I think it's a really important area. So the technical work that we do, as you've seen, we've got quite a few technical work groups, and we have joint alliances with other organizations like the NVM Express, JEDEC, Open Fabrics Alliance, OCP. And there's a wide variety of outreach and evangelization we do via the SIGs, or the tech marketing pieces. We do webcasts like this, and we were going to be doing a webcast. And in fact, I'm going to answer one of the questions that came through just a few seconds ago when you get the chance, I'd appreciate a few more words on computational storage and composable storage differences. Is one a subset of the other? And we're going to answer the question today. I think we could actually turn that into a really good Bright Talk session where we talk about computational storage and composable storage and point out the differences and the similarities and how these things can be screwed together. So that's thanks for the question, because that's giving me a really good idea about a presentation that we do next. I think the other thing that's really important to note is that you can join us. This is not a club exclusively for people who are already members. We're always looking for companies and individuals that are interested in progressing SNIA's core messaging and value, which is to try and educate and bring as much as we can in terms of taking technical work that technical work groups do and making sure people understand its application out there in the real world. So, that's one of the things that we really pride ourselves on, is all the outreach and evangelization that we do and moving that forward. So, where to find out more? There's a big list of stuff here. We'll make sure that you get this presentation on the website. I'm not quite sure what it is. Educational materials. Under the link Educational Materials, you'll find that you can get access to the content of this presentation today. That's SNIA.org/educational-library. Now, there are a couple of other questions, and I'm going to take the opportunity, since we've got a couple of minutes spare, just to ask, and I think one of them is for Jim. There's a PMDK for PM in Oracle Solaris, question mark.
Yeah, it's so the question, at least that I saw come across, is there a PMDK port for Solaris? The answer is currently no. The response that I've gotten when I asked that is that somebody should submit a pull request if there's a desire for that at pmdk.org, and very likely that would be put into consideration. But PMDK itself is entirely open source, and so if there was interest in a Solaris port, I'm sure that the source could pretty easily be ported. Given the close similarities between Linux libraries and Solaris libraries, I think it would be fairly easy to do.
Okay, good. One last quick one for Ellie. So you're going to have to come off mute, Ellie. Does deduplication technologies come into play with computational storage? CPU power is cheap, but storage is still very expensive. So I suspect the question is, are we doing computational storage devices that are going to do dedupe?
Not as far as I know. So yeah, you can dedupe on SSDs as block storage device. I don't see how computational storage can help. Remember that once you have the compute on storage, then the compute can be done on the data that is on that storage. If it's a CSD, if it is an accelerator, maybe a dedupe can do. So let me get back to you on this one with a more complete answer.
Okay, we'll answer these questions on the blog as well. And there's one I'm going to answer really quickly with a simple one-word answer. So the question is, magnetic hard drives are persistent storage. Is there really that much difference in how the OSs should handle newer non-volatile memory? And the answer is a big, fat yes. There's a huge difference. Go out to the website.
See, I'd have gone with absolutely, but yes works too.
Yeah. Go out to that persistent memory part of the SNIA website, and you can get all the information of why non-volatile memory is such different stuff. It really is. So, I would like to thank today, I'd like to thank Ellie Tiomkin from NGD Systems. I'd like to thank Jonmichael Hans from Intel. And I'd like to thank Jim Pfister, who represents SNIA Contracting. Thank you very much, all three of you today, for coming along and presenting. And thank you, the audience. And remember, we are here to talk about computational storage. We're here to talk about persistent memory, and we're here to talk about SSDs. Please join us in the group. Thank you very much indeed.